Welcome back. Last section in chapter 18 on integration. Definite integrals. Okay, so first of all, what is an indefinite integral? An indefinite integral. Indefinite integral are what we've been looking at all along to date. An integral of some function dx. Okay, that's an indefinite integral. A definite integral looks almost exactly the same, except it has a beginning point and an end point to that integral. So a 2b of f of x dx. Okay, so by an end point and a beginning point, those are x values which we are going to evaluate on the graph or algebraically. Okay, so remember we talked about I've got these upside down. Going to change these around. I got them in the wrong order. Okay, we talked earlier about the fundamental theorem of calculus. So the fundamental theorem of calculus states that if we know what a derivative function is, we can calculate the original function by integrating, but in fact we could come up with a numerical answer for a definite integral if we know what these values a and b are. Once we integrate, we take that integral, the original function, substitute in b for x because b is on top, and then subtract that from substituting a in for f because a is on the bottom. And we will end up with a numerical answer. So what this looks like graphically is if we have a graph, say we have a graph of a straight line. Okay, I'm just going to use, I'm not going to use numbers in here, I'm just going to use the concept. So we've got a linear function. So we know that the integral of a linear function will be a quadratic function. That exponent has to increase by 1. So the quadratic integral that goes with this may look like that. Okay? Now, if we're looking at that integral as a definite integral, we're looking for certain points from a to b. A might be here. B might be here. Okay? Then we are looking at that integral from here to here. So we're looking at this part of the graph in particular. Okay, so that's what a definite integral means. Whereas the indefinite integral is talking about this entire function. Okay, it's common to write capital F of b minus capital F of a this way. So that when we're integrating a definite integral, we have this function, and we'll do some examples so you'll see what I mean. We could, this is the integral, the original function, okay? And then we can get rid of this and this and replace it with those square brackets and this b and a here so that we know we then need to do this. Okay, so I'll show you what I mean with some examples. Now, keeping in mind that we have these properties of integrals here. We looked at them earlier in the chapter. So we've got these properties of integrals. If I have an integral from a to b, okay, that is going to be actually the same as the negative of that integral from b to a. Okay, so those two numerical answers will be negatives of each other because they're going in the opposite direction. If I have a constant here, c, I can pull that constant out. I did that with indefinite integrals, I can also do it with definite integrals. If I have an integral from a to b here, and then add that, we're dealing with the same function, add that to the integral from b to c, well, it makes sense that that would be equal to that integral from a to c, all the way from a to c. So again, we might have a graph. This might be the function we're looking at. This might be a, b, c. So we're talking about the integral from here to here on the first part, plus the integral from here to here. Well, that equals all the way from a to c. And lastly, we've got this integral f of x plus g of x from a to b. We can separate that out as f of x and g of x, just like we could in indefinite integrals. So some properties to keep in mind as we move along.